Relativity is just a way for two people to agree on what they see from different perspectives. One of the most obvious examples of relativity is our perception of relative distance. Buildings appear smaller when they are further away. Even from the same distance, objects can appear different depending on the perspective. Looking at a house from the corner makes the sides seem to be shorter than if we look at the same house straight on. Relativity allows us to agree on the size of the building regardless of the distance or the perspective from which they are observed. Relativity gets a little more complex when motion is involved. Classical relativity provides a way for two people to agree on what they see if one of those people is moving. Two people can observe the same event as being different depending on their perspective. Imagine going for a drive with your best friend. It's a long drive, so be sure to bring a thermos of coffee. If you are driving at a constant velocity of 65 miles per hour straight down a stretch of highway, you can easily pour a cup of coffee. Now this is possible because the car, you, the thermos, the coffee, and your cup are all traveling at a constant velocity. From the perspective of you and your friend, the coffee is not moving, and thus appears to have a velocity of 0 miles per hour. If someone were watching you drive by, he would observe the coffee moving at a velocity of 65 miles per hour. That is the same velocity of the car. Both perspectives are correct. The coffee is moving at 0 miles per hour relative to the car and 65 miles per hour relative to the road. As 65 miles per hour is not the same as 0 miles per hour, it is not enough to ask how fast something is moving. We must ask how fast an object is moving relative to something else. In other words, motion is relative. If you are viewing this video while sitting or standing still, you're traveling at 0 miles per hour relative to the ground. However, the Earth is spinning on its axis at 1,000 miles per hour. Additionally, the Earth is rotating around the Sun, and the Sun is moving around our galaxy. Now that's a lot of motion. To say that you are not moving when sitting still is accurate, but only relative to the ground. Let's look at a bit more complex situation. Imagine playing catch with your best friend on the back of a truck traveling at 65 miles per hour down that same straight stretch of highway. Bring your coach along and have him measure the velocity of the ball using a radar gun. As you play catch, your coach clocks you throwing the ball at 50 miles per hour. Your coach then clocks your friend throwing the ball at 40 miles per hour. What do these speeds mean in terms of relativity? You threw the ball with a velocity of 50 miles per hour relative to the truck, and your friend threw the ball with a velocity of 40 miles per hour relative to the truck. Now let's consider what happens if the coach clocks the ball velocity from the roadside. Remember, the truck, along with everything on it, is traveling forward with a velocity of 65 miles per hour. When you throw in the same direction as the truck is moving, the velocity of the ball is added to the velocity of the truck. Your coach will measure the ball's velocity at 115 miles per hour if he is standing on the side of the road. Wow, that's fast. More accurately, the ball is moving with a velocity of 115 miles per hour relative to the road. How fast will your coach observe your friend's throw? Well, as the ball is moving in the opposite direction of the truck, the velocity will be measured at 25 miles per hour. More accurately, the ball's velocity is 25 miles per hour relative to the road where the coach makes his measurement. The velocity of the ball is subtracted from the velocity of the truck as they are moving in opposite directions. Classical relativity applies to almost everything we observe in our daily lives. This includes walking on a sidewalk, running in a race, moving automobiles, and even fast-moving jets. However, classical relativity breaks down when it comes to extremely high speeds. classical relativity does not apply to light, which moves at a speed of 186,283 miles per second. That's almost 300,000 kilometers per second. This velocity is the same regardless of the motion of the source or the observer. So in summary, classical relativity provides a way for two people to agree on what they see if one of the people is moving. Objects in motion have velocity which changes depending on the observer's perspective. To accurately describe the velocity of an object, it must be phrased relative to some other object. Two objects moving together with the same velocity have no velocity relative to each other. A stationary observer will perceive the object moving at the same velocity. If objects are moving together at a constant velocity, their velocity relative to each other is zero. Velocities can be added or subtracted from each other to determine the relative velocity of an object. Objects moving at the speed of light do not follow classical relativity. Their velocity is 300,000 kilometers per second relative to any observer, stationary or moving.